Hi, I am Mini from EC department. Now I am going to explain the topic transistor biasing. Right? First we should know what is meant by biasing. What is meant by biasing? That means applying DC voltage to a circuit. It's the simple meaning for biasing, right? So biasing is the process of applying direct current, voltage or current to an electronic component such as transistor, diode or vacuum tube. This is what biasing. Okay. For what purpose we are using this biasing? To set the proper operating point. We can say this operating point is otherwise called as Q point or quiescent point. Okay. Now in this transistor biasing, this biasing is primarily used for amplification. What is amplifier or amplification? Amplification is used to improve the weak signal to the strong signal, right? This normally a transistor is a non-linear device. That means that voltage and current is not proportional. We all know the Ohm's law, isn't it? Ohm's law, that is V directly proportional to IR. So here this if it is non-linear device, it does not follow this Ohm's law. Okay. By reducing the fixed DC voltage to the base, set the transistor operating point within its active region. Okay. So what is that active region, cutoff region or saturation region? Normally these transistors are operated in three regions, namely cutoff, active region and saturation region. Cutoff, and the name itself, cutoff means the transistor is in off state, we can say that is cutoff state. Okay, so how we identify this? The transistor input, commonly we are used, so many configurations are there: common base, common emitter, common collector. Regarding that, only common emitter configuration is used as an amplifier because its voltage gain and current gain is high. At the same time, it have good coupling. How it have good coupling? Due to the ratio of output resistance to input resistance is high. Okay, so due to this reason it is good coupling. We can say this common emitter configuration as an amplifier. Okay, now what is the input of common emitter? In common emitter, the input is base. What about the output? It is collector. Emitter is common for both. Okay, so the input must be forward bias and the output must be reverse bias. If this condition satisfied, the transistor is operated in active region. Here what is cutoff region? That means off state, no? So both input side as well as the output side, both will be reverse bias. So we can say that as a cutoff region. Okay, the transistor is operated in off state. What about saturation region? That is fully on. Simply we remember it is fully on. So the input as well as output both should be forward bias. We can say that as a saturation region. Okay, to operate the transistor in the desired region, we have to apply the external DC voltage of correct polarity and magnitude to the two junctions of the transistor. Okay, so the basic purpose of transistor biasing is to keep the base emitter junction should be forward biased and collector base junction should be reverse biased. So this is the main condition for transistor biasing. Okay, now need for biasing. Why biasing is important? It ensures stable operation, it prevents distortion and keep the transistor in active region, and it improves amplifier performance. For these reasons this biasing is important. Okay, so what is that? Ensure stable operation. If the transistor is operated under stable condition, we will get the proper output. Otherwise, in some situations it may be positive clipping or negative clipping. This is for unstable condition. Okay, so if it is positive clipping or negative clipping, we are unable to receive the original signal. Okay, so that's why this biasing is very important. In another way, it prevents the distortion. So many distortions, distortion is in a sense that that is disturbance. Okay, so if the transistor is in active region, or the Q point should be in the center of the active region, we will get the proper output. Okay, so if it is not biased correctly, it would work inefficiently and produce distortion in the output signal. Operating point should not be affected due to temperature changes and device variations. Now, various applications of transistor biased. Already told that three regions are there. The transistor should be present in three regions. What are they? Cutoff, active and saturation. So that condition, okay, see the table, what's happened there? Three regions are there, right? Cutoff region, active region and saturation region. For emitter based junction, this is the here we are taken that common emitter amplifier. The input is base emitter and the output is taken from collector base junction, right? So in emitter base junction, if it is reverse biased and the output is reverse biased, that is both should be reverse biased, the transistor is operated in cutoff region, right? So where we applied these type of conditions, switch. Okay, next one, if input is forward biased and the output is reverse biased, now the transistor is operated in active region. Here where we applied this, if we need the amplifier, we can use like this way. Okay, then the next one is saturation. Here also the input is forward biased and the output also forward biased. Okay, both should be forward biased. In this case, the transistor is operated in saturation region, and where we used this also act as a switch. Okay, next, some of the factors which will affect the operating point. Okay, what are the factors which will which will affect the operating point? Actually, the point obtained on the DC load line by the value IC and VCE when no signal is applied at the input is known as operating point. You know, load line. What is load line? It's the straight line. We can choose two values here. The two values are IC and VCE. Okay, now two types of load line also, AC load line and DC load line. So these load lines are used to used the transistor as an amplifier. Okay, so first one, DC load line. If we are not apply any input, we can say that transistor is in DC load line. If we apply the input signal, that time the transistor is operated at AC signal or AC input. Okay, now what are the factors which will affect the transistor? Stability of the operating point, or it will affect this that is the transistor is not constantly maintained. So what are the factors? Temperature dependence of IC, change of VBE and beta due to replacement of transistor, and thermal runaway. Okay, so temperature dependence of IC, next change of VBE and beta due to replacement of transistor and thermal runaway. Then next one, stabilization. What is stabilization? The process of making operating point independent of temperature changes or variations in transistor parameters, which is known as stabilization. Okay, when the temperature changes or when the transistor is replaced by same type, the operating point also changes. Okay, for faithful amplification it's essential that operating point remains fixed. This necessitates to make the operating point independent of these variations. This is known as stabilization. Then next one, need for stabilization. So as we see in stabilization, why the stabilization is needed in biasing for various dependencies. Okay, if it is temperature dependence of IC, this is the standard equation of collector current which is present in common emitter. IC is equal to beta IB plus 1 plus beta into ICBO. Beta is the parameter and ICBO is the leakage current, or we can say that if the emitter is open, okay, so collector to base leakage current. Okay, so this is the condition, this is the standard equation which are used in normally we are used in derivations section. Okay, the above three variables are strongly temperature dependent. Hence, with the increase in temperature, if any of these parameter changes, then collector current also changes. So operating point is shifted to any other region. It may be cutoff region or saturation region. It is not present in the active region. Okay, now next one, variation in parameters. If the parameter, so what are the transistor parameters? Three values. Okay, what are they? Beta, ICO, VB. These are the transistor parameters. If the value of beta is changed, it will shift the operating point in any undesired region. That indicates that cutoff region or saturation region. What is thermal runaway? Okay, what is thermal runaway? Thermal runaway is the condition where a transistor gets overheated due to increasing current, and this keeps repeating, leading to damage. Okay, actually thermal indicates that temperature. So runaway, we will remove that temperature. If the temperature increases, what happened? The transistor may be destroyed or damaged. Okay, why it happens? If the temperature increases, the collector current increases, so more current will flow there and more heat produces. Due to this more heat, this forms one loop. Okay, again and again it happened. That is what thermal runaway. So how it causes in BJT? Leakage due to increase in leakage current or decrease in base emitter voltage or poor heat dissipation. So what are the effects due to this thermal runaway? Overheating, loss of stability, and transistor may be damaged. Okay, how to prevent this? Use heat sinks. If you use heat sinks, we can prevent that thermal runaway, and it provide proper biasing. Use negative feedback circuits. Choose components with thermal stability. What is that feedback? Feedback means a portion of output is given to the input. That is what feedback. Okay, so this is what thermal runaway. And here see, if the temperature changes, then ICBO changes, which turn changes IC and operating point. Flow of collector current in the collector circuit produces heat at the collector junction. This raises the temperature. Hence, ICBO increases, which in turn increases collector junction, and the whole process repeats again. Such successive increase in IC will drive the operating point into saturation region. This process is also called thermal runaway. Okay, this is very dangerous situation because due to excessive heat, the temperature may burn out. Okay, next one, bias stability. What is that bias stability? It's necessary that IC should be kept constant. Okay, due to the variation of ICBO and ICO. Okay, so in order to maintain this ICS constant, okay, so we use the stability factors. What are the stability factors? S, S dash, S double dash. Okay, so S indicates that all the numerator terms of dou IC. Okay, if it is S or S dash or S double dash. Okay, so S is equal to dou IC divided by, you know, the transistor parameters ICO, VBE, beta. Okay, so here S is equal to dou IC divided by dou ICO. Then S dash is dou IC divided by dou VBE, and S double dash is dou IC divided by dou beta. Okay, these are the stability factors. Okay, so see the condition here, S equal to dou IC divided by dou ICO. So what are the remaining parameters? Beta and ICBO are constant. Okay, so any change in collector leakage current changes the collector. The stability factor should be low as possible so that the collector current does not get affected. Okay, now negative feedback. So you all know what is feedback. The part of output is fed back to the input. So due to the feedback, the output we may be modified. Okay, so if there is no feedback, okay, whatever input is given to that particular block, we get the output as it is. Okay, but if we are using feedback, okay, what happened, the output may be modified, so we get the desired output. Okay, so here the negative feedback, if the original input signal and the feedback signal are out of phase, that is 180-degree out of phase, then it is called negative feedback. It's used in amplifiers. Okay, next, negative feedback reduces the gain of the amplifiers. So this is one of the main characteristics which is present in negative feedback. It reduces the gain of the amplifier, but still it is employed in almost all the amplifier circuits. Okay, it's because the negative feedback improves the overall performance and stability of an amplifier. Okay, next one. Types of transistor biasing. There are so many types of transistor biasing. So what are the types? The first one is fixed bias, next one collector to base bias, and third one voltage divider bias. The last one is emitter bias. So what is the other name of fixed bias? That is single base resistance method or base bias. Okay, then next one is, okay, in this first we see about the fixed bias or single base resistor bias or base bias. These are the other names. Okay, so actually in this fixed bias, the resistance RB is connected between supply and the base. Okay, the record zero signal, or we are not giving any input signal. Okay, the base current is provided by VCC, and that VCC keeps the base emitter junction forward biased and the collector base junction reverse biased. So if the transistor is operated in active region, then only we get the proper output, right? That's why the input base emitter junction is forward biased and the output collector base junction is reverse biased. Okay, now see the circuit diagram. This is the circuit diagram of fixed bias. So first we draw the common emitter symbol. Okay, so what are the terminals present here? Base, emitter and collector. Okay, yeah. Now, so we are applied the input through the base and take the output from collector. The emitter region is grounded. Okay, yeah? Now the base resistor is fixed. That's why we will say that it's the fixed bias or base resistor method. Okay, so how to solve this? So first we will find the value for IB. How will you find the value of IB? Apply KVL to the base side. Okay. How will you apply the base side KVL? See the circuit diagram. This is the input side, right? In this input side, VCC, how to apply VCC minus IB into RB minus VBE equal to 0. This is the way you have to apply KVL to the input side. What is that KVL? Kirchhoff's voltage law. What it states that? Simply you remember that rise is equal to drop. If the polarity from minus to plus, it becomes rise. Okay. If the polarity is plus to minus, it becomes drop. Okay, so that's why in this equation VCC minus IB into RB minus VB equal to 0. So we need the IB value, no? So keep the IB value in single place and remaining all the terms are given to the another, that is LHS or RHS. Okay, so now the value is IB is equal to VCC minus VB divided by RB. Okay, now we have one condition, this VCC is greater than VB, because this VB is the potential barrier. If it is silicon material, the value is 0.7. If it is germanium, silicon is 0.7 and germanium is 0.3. Okay, so that value is very low compared to VCC. So we can neglect that value. If it is low or high, we will neglect, right? That's the way. Here also we will neglect that. So remaining term IB is equal to VCC by RB. Okay, so see the condition for silicon transistor, VB value is 0.7 volt and germanium it may be 0.3. Okay, so generally we are used to this silicon transistor only we are used. Okay, here the supply voltage is fixed but RB is selected, IB is also fixed. Now next case, what's the next one? Second type of biasing, collector to base bias, or we can say feedback. Okay, we are taken the output from output side to the input. Okay, now we apply the KVL to the collector to base circuit. So what are the advantages of fixed? Before that, we should know what are the advantages of fixed bias. It's simple circuit. The circuit is very easy to draw. That's why we can say the circuit is very simple. And the operating point can be fixed anywhere in the active region of the characteristics by simply changing the value of RB. Then the biasing conditions are set easily, no loading effect as no resistor is present at base emitter junction, and due to their simplicity fixed bias circuits are cost effective. Okay, then the next one, disadvantages. What are the disadvantages of fixed bias circuit? It's poor thermal stability. Thermal means temperature, right? Heat. Okay, so its stability is poor, and IC equal to beta into IB is already fixed. This IC depends on beta, which is different for same type of transistor, and shift the operating point. Okay, adjusting the operating point over a wide range may be challenging with fixed bias. It will limiting its suitability for certain application, and it is potential for thermal runaway, and limited temperature compensation leads to changes in bias point. And the next one, collector to base bias. See the circuit diagram. Okay, here what's the main difference between fixed bias and collector to base bias? There we are taken the RB value through the VCC. Okay, but here the output is collector side taken from out collector. From this we use the base resistor to the input of the transistor. Okay, now what about the two capacitors we are connected, right? Input side and output side, this is the coupling capacitors we are connected. Okay, now apply here also we will find that value. How will you find? Apply KVL to the base side. Okay, so by applying base side, VCC minus IC into RC, that is two currents are flow through this RC resistor. Okay, so what are the currents flows through the RC resistor? IC plus IB. Then remaining comes over the base side, IB into RB plus VB. Okay, so VCC equal to, so from this equation we need the IB value, no? So we know the relation IC equal to beta IB. Using that relation we will get that IB is equal to VCC minus VB divided by 1 plus beta into RC plus RB. If you want to find the IC value, apply KVL to the output side. So we will get that output value. Okay, now apply the stability factors. You know there's so many stability factors, substitute there and find the values. Okay, now the next one is what? Advantages. What are the advantages of base bias or collector to base bias or feedback bias? It's simple circuit. It's also simple, but it provides some stabilization of the operating point. It needs only one resistor at base. Reduced sensitivity to transistor variations, lower sensitivity to the power supply changes. Okay. Now disadvantages. What are the disadvantages of collector to base bias? It does not provide good stabilization because stability factor is high. It provides negative feedback which reduces the gain of the amplifier, and it's depend on component matching. It's more complex in comparison to fixed bias circuit. Restricted utilization in certain applications with specific voltage requirement. Okay. Next, voltage divider bias. So what is that voltage divider bias? This is the third type of biasing which is present in transistor biasing, right? In voltage divider bias, we are used to two resistors. What is the purpose of resistor? To resist the flow of current, right? So here this R1 and R2 are divided. There is the voltage drop across R2 and the input must be forward bias. This R1 and R2 resistors act as voltage divider. Okay. This is most widely used biasing method that provides biasing and stabilization to a transistor. Then this is the circuit diagram of what? Voltage divider bias. In this voltage divider bias, see the diagram. What's the difference between other two from base resistor? In base side only one resistor used, right? Collector to base bias. From collector to base we are connecting one resistor as feedback, that is our connected to collector to base bias. But here only the resistors are divided, R1 and R2. Okay. Then the next one, here also same procedure to find the stability factor. First apply KVL to the input side for finding IB and apply KVL to the output side for finding output side. Okay. Then advantages. What are the advantages of voltage divider bias? IC in the circuit is almost independent of transistor parameters, and the transistor employed in the emitter provides stabilization. Its most prominent one, flexibility in adjusting operating point, moderate sensitivity to power supply changes. Okay. Then the disadvantages. What are the disadvantages of voltage divider bias? The signal tends to get mixed up. It requires more components, and due to increased complexity, it is more expensive. It leads to reduction in overall circuit efficiency due to the power dissipation. Okay. Then and the next one is modified fixed bias. So in this modified fixed bias, you have to add one emitter resistor in the emitter side. Why this is done? To improve the stability of the circuit. Okay, in order to improve the stability, we are modified the circuit. Okay, here also same procedure to analyze it. Then if you apply KVL to the input side to find IB and apply KVL to the output side, that is what? to find the output side, okay, output current. And advantages, what are the advantages? We are used on extra emitter resistance, right? It provides stability and it provides high voltage gain. Actually, it's a simple circuit with enhanced stabilization, reduced sensitivity, and uh, it gives the balance between simplicity and performance. Then what about the disadvantages? Its operating point can be affected by change in temperature, and it requires the use of dual polarity power supply and limited voltage range, potential for component matching and complex circuit. Okay, then this is the table we finally given to that. So we know that three types of biasing that are mentioned in the table like this: fixed bias, collector to base bias, voltage divider bias, finally emitter bias, right? Then in fixed bias, actually what happened, beta is dependent and the stable Q point is unstable. Where we applied this fixed bias, digital switch, okay. Then next one is collector to base bias. In this collector to base bias, what is the parameter analysis here? Greater stability. Where we used it, an amplifier. Next one, voltage divider bias. Here the beta is independent and the Q point is stable. This is also used as an amplifier. Next one, emitter bias circuit. This is also greater stability, and it where we apply this emitter bias circuit, IC driver amplifier. Okay, then conclusion. So biasing is necessary to keep the transistor in its active region where it can amplify signals without distortion. So finally we review all the things. What is that biasing? Biasing is external supply, okay, external DC supply which is given to the electronic devices. For what purpose of using this? To set the proper operating point. Commonly it's used in transistors like BJT and MOSFET, okay. Why this biasing is important? Ensure stable operation, prevent distortion, keeps the transistor in active region, improves the amplifier performance, okay. So some of the operating regions of transistor is cutoff region, active region, saturation region, okay. So this biasing keeps the transistor in the active region, okay. So cutoff region, it may be off state, and active region for amplification and saturation region for fully on. So many types of biasing are there: fixed bias, collector to base bias, voltage divider bias. So compared to other two, voltage divider bias is very important, okay. In that fixed bias circuit, the circuit is very simple, easy to design but not stable, okay. So it's not suitable for practical applications. And voltage divider bias is commonly used method. It uses two resistors, it provides good stability, okay. This voltage divider bias gives stable Q point. This Q point means what? Operating point or quiescent point. It must be in the middle of the active region. If we are given the proper biasing, the output is stable and no signal distortion, better efficiency and longer device life, okay. So biasing is very essential for transistor operation. It helps in amplification, ensures stability and performance, okay. So what is the real-time example for this? Just think about that. If you are playing the music, before playing that music, we set the volume level, right? So that is what biasing. If the volume is too low, there is no sound. If the volume is too high, there is the distortion. If it is correct level, you will get the clear audible, okay. So same way biasing sets the correct level for transistor operation, okay. I think you all familiar in that. Thank you.